Hi, good afternoon. Hopefully everyone had a good lunch break. Super excited to be here, GopherCon 2023. So thank you all for attending my session. Today we will cover a really exciting use case going over some Go microservices for machine learning at the edge. And my name is Samantha Coyle. I'll cover a few different sections here, starting out with an introduction, going into an architectural overview, covering some use case specific Go packages to include service coordination, deployment, testing, and internationalization, which was really fun. So that is the supporting of multiple languages. And we'll wrap things up from there. So as I mentioned, I'm Sam. I am a software engineer at Diagrid, where we work to boost developer productivity by providing tools and APIs for building cloud-native applications. I also get the opportunity to work on the Dapper open source project, which is super fun and exciting. And this presentation will cover some of my work with the Jedi team at Intel. You can see the team of Gophers there, where I have Neethu up at the top just because she is my right-hand gal and someone who has given me some really good feedback on this presentation. All right, are y'all ready? Woo, thanks for the excitement, y'all. So I'll be walking through the different phases of the software development lifecycle as I go through the different sections of my presentation, naturally starting with the introduction and the planning and analysis of this project. So who loves Go? Yeah, everyone should be raising their hands, so wake up, we're after lunch. You can see here on the Go website, we have a lot of really great use cases when it comes to Go. There's a lot of great that comes with Go, thanks to its simplicity, strong standard library, and excellent performance that makes it really great for a lot of awesome use cases. Down to at the bottom, we have site reliability engineering, and even building web servers, APIs, and our typical microservices. So has anyone in the room worked on a Go project enabling data processing or a data pipeline? All right, some shy hands, some excited hands, thank y'all. I am proposing with this talk and with this use case we'll be covering, I think Go has room in the data processing to make it a really strong use case, right? So Go has a lot of great when it comes to portability, tooling, ease of use, and a lightweight footprint that I think makes it really great for data processing. So hopefully y'all will agree with me by the end of this presentation. At a very, very high level, we'll be covering data processing for a healthcare use case where we have input and we have output coming out, right? And in between, we have some machine learning processing using existing models. So we are not training models here. We are simply taking cellular images from a microscope, applying some machine learning, and then getting some output, right, for maybe prognosis or even some sort of treatment outcomes. So this is in the biopharma sector, which is really, really exciting. Some nice collaborations between Intel and a company called Beckman Coulter, who are really big players in the biopharma industry. This project was on cellular virtual staining. I know it sounds really cool. But basically, in this lab, right, we have these bench scientists, and they're working with these microscopes with these cellular images. And what you would typically see done is physical staining, which actually can ruin the specimen in order to see if there are any image anomalies going on in the cells. So our project is working at applying machine learning to enable that virtual staining to preserve that biospecimen. So I think it's pretty cool. And again, it's getting at image anomaly detection for those cells, as well as edge pipeline enablement in this laboratory. So at its whole, this is a data processing pipeline that preserves biomedical specimen using Go. So really fun use case. Our project can be broken down into 4 main steps. We have a microscope with some bench scientists working with it. We have cellular images for our input. We have some processing going on. And then we have outputs. That is the 4 main pieces of our project. That enables a Go data processing where we can get some prognosis and potential treatment outcomes, or even just some results on those images, right? All right, now that y'all know it's a healthcare use case, really cool project, let's go ahead and dive into the architectural overview. So that brings us to the next phase of the software development lifecycle for the product architecture. And before I share with y'all a few slides on what that looks like visually, I want to go over some of the terminology just to make sure we're all on the same page. So have y'all heard of terms data plane and control plane? I see a lot of nodding heads, so our project is no different. There's a data plane, which is the image capturing device services. So when I say at the edge, right, we're talking about these microscopes that are doing some processing. So this is within the laboratory environment, and we called this the OEM, or the original equipment manufacturer. Or you can call it the data plane, right? A different machine. We also had the control plane, which is where the brains of the operation lives. This is where our model inferencing services for those input images happens. We called this the gateway. Then we had a pipeline. So this is AI-assisted image pre-processing and inferencing. We have jobs, which process things as they track through the system. And then we have tasks, which match jobs to a pipeline. So if you don't remember all of that, that's fine. I will show you visually. OK, and real quick, too, all of our microservices for this solution, we're using EdgeX Foundry. This is an open source project hosted by LF Edge, or the Linux Foundation. It is what the Internet of Things group within Intel would typically use for our framework for our microservice development using Go. So again, it's that framework for IoT edge compute. And it enables an application service API, so we could easily communicate with PubSub, state stores, work with some security using EdgeX, and so forth. So kind of honing in a bit more visually of what we're going to be talking about here today. We had our data plane on the left, and this was our OEM machine running Windows. Windows, not Linux. And we had a few services there running as executables with our microscope. And then we had our control plane, which you see is a bit busier in that box because it is the brains of the operation. We have a few more services running with Docker this time. Then we have a black box for machine learning processing. So I will very much treat that like a black box. And if y'all want more information, this was touched on in a prior presentation earlier this year. So I'll give y'all info on that later. And the control plane was running Linux. So keep that in mind. And our data plane was generating these cellular images, right? But something that we wanted to keep in mind was having a flexible and scalable and adaptable architecture where we weren't constrained to just microscopic cellular images. We wanted to support something like maybe brain scan images or MRI imaging, right? So we wanted it to be adaptable. And so we would generate these images, pass it off to the control plane, do our processing, get our output, and that was it. So I'm going to cover the legend and what this looks like before I share with y'all what the different microservices looked like. The data plane is on the left, control plane on the right. The legend includes a few pieces. Dark blue will be our microservices. Light blue are the EdgeX application services that interact with different EdgeX components. We had a file system on both sides that are in green. Purple are EdgeX components. Red includes the TCP requests to our database. And then light blue will be HTTP requests. So are y'all ready to see the data plane? All right. First things first, we need some images. So our microscope would generate these images, save it to that file system. We then had the file watcher microservice in step 2 watching these folders and making RESTful calls to our data organizer, letting it know, hey, I've picked up on an image. Step 3, There then are routes called over to our data or our control plane where it's saying, hey, I have some jobs coming in. We're going to need to do some processing here soon. Step 4, our file sender will send over the job and file information to our control plane where we will then do processing. And step 5, that file receiver on the data plane is subscribed and will pull the output files after processing occurred. So we had firewall rule restrictions due to some like laboratory equipment and the cellular images that they needed to protect. So we had to think about a polling system here. Then on the control plane side of things, this is where a lot of the effort was going into, right? The processing. So step 1, that job repository is going to create a job in Redis for an input image. We then have the task launcher for step 2, verifying that there's a matching task. So it's basically saying, hey, there's an input image. Do I have a pipeline to run? We then will send over the job and file information from the data plane to the control plane and write that to the green, which is the file system. From there, we have step 4, where the task launcher is sending this information via the MQTT message bus off to pipeline execution. We have some pipeline processing occurring, again, that black box scenario. We have, in step 6, the outputs saved to the file system on the control plane. And then step 7, transfer that back. So this is our architecture in a nutshell. We've covered the data plane, we've covered the control plane. So y'all want to see what that looks like together? Y'all are so excited, thank you. All right, this is going to be a video, and hopefully I don't lose my breath talking through it. So we will have input images dropped in from the microscope, copied to the file system. The data plane is fixing to contact our control plane. We then check in Redis if we have associated pipelines to run for that input image. Then the file sender on the data plane is fixing to send over our input file and job information over to the control plane. We have the file receiver saving that file to the input folder on our control plane. The task launcher gives this information to the pipeline execution module in just a second via MQTT. Pipeline is then executed in that black box, and inference occurs where an output is generated and stored within our output folder on the control plane. And now communication is going to occur between the two systems, and the file receiver on the data plane will ask for the output file right now to be sent back. And then finally, the output is stored in green in the file system on the data plane. So that is it in a nutshell. Now you can kind of see the flow of everything. And just to kind of give you a bird's eye view, pun intended, of what we just saw, right? We have the data plane with the inputs. They're passed over to our control plane in step 1. There's outputs that are generated from machine learning processing, sent back to the data plane. And then on our control plane, that step 3 is an archival process, being mindful of resource consumption and how many files we're generating. Now that we've talked about the architecture, we'll go ahead and look into service coordination, just because we had a lot of microservices. We had 2 systems running 2 operating systems, and so we needed to be mindful of how do we make sure they're coordinating, how do we make sure that our dependencies are up before our actual services will accept requests. So all of that fun stuff for our healthcare use case. So that brings us to the fun part, which is develop and code, right, of our software development lifecycle. So this brings us the need to wait for our dependencies and those dependent services. We had a few different considerations with respect to maybe there are deployment time differences across the installation in a laboratory versus the installation maybe in the cloud. We wanted to be mindful of, are there communication issues between those machines? We mentioned there was a firewall rule restriction, so would there be any other things we didn't anticipate? There also could be just service startup related issues, maybe intermittent issues with one service that impacts the availability of a different one, right? Just some common considerations that we wanted to think about from a perspective of service coordination, but also being mindful of applying that to our testing services, right? So there were all of these what ifs in between going on, in our architecture with respect to service coordination. And that kind of brings us to two different implementation layers, one of which is kind of at that build layer on a Docker side of things, the other, the Go application layer. So how many of y'all have done service coordination, waiting for services, say in the build layer? Okay, all right, some hands. So this might be something like the Docker Compose, depends on keyword, or maybe in the Docker layer you have a wrapper in your entry point, such as the Vishnu Bob Bash script, where you specify a TCP host and port, and you say, wait for this other service before I start. So do y'all remember a caveat I said to our data plane as to why one of these will not work? All right, all right. So we didn't have Docker installed on the data plane, so we wanted to be mindful of the restrictions that we had, right, and what we wanted our customers to install, and so we went with the Go application layer approach here. And so looking into what were some of our Go packages available for service coordination and waiting for the host and port availability of our dependent services, that brought us to two packages, and we actually went with wait for it. And we went with that because it is much more of a maintained package, which was a bit of a requirement for us at Intel. The features here, it does allow you to wait for the availability of TCP hosts and ports for those dependent services. And the nice thing here is our team had previously been using that Vishnu Bob Bash script for our Docker layer, waiting for our dependent services. So it was heavily inspired by that script. So it gave us the same look and feel for this Go application layer implementation. And the really nice thing is, we were starting to look into the logic. We can see here an exported function called wait. It's really easy to understand, like, hey, this is going to wait for all of our services that are dependencies before actually starting our service. So it looks good. But naturally, I have challenges and learnings to share with everyone. And so, does anyone see anything wrong with this slide? Yeah, I mean, it looks fine to me. But the limitation is it was contained under package main, and so you can't consume from other people's package main, right? So we couldn't use this. We had to bring in this logic into our project, like literally copy paste it in, which was really unfortunate, while giving attributions to that originating author. So kind of a bummer, but it is what it is. And so we brought that in, made a package wait that we could actually consume from, and thus a consumable function was created. So this packaged setup enabled us a way to bootstrap our main.gos, where we would force our controller to wait for dependencies, and it would wait for a specified amount of time that we had in our configuration, and if the dependencies never became available, then our service would exit, logging the failure. And so naturally, we all like open source, right? Right? So we contributed back to this project, and there's an open PR out there and an ongoing collaboration effort. So when I brought this back into the open source project, I actually added in some retry logic because that's what we wanted for our project in case there were intermittent issues or transient issues. So we wanted it to retry. So we're kind of having some conversations on that front, as well as the classic tale of it works for me, but not the author. So that's fun, right? So ongoing collaboration. And there were other learnings as well. It's, number one, good to have options when it comes to these sort of things. And what makes sense for some might not make sense for everyone. So wait for it was okay for us, but that might not make sense for y'all. And nothing is perfect. We know that with software. But open source is awesome, but it can take some time to improve the community, improve the tooling. You just have to be patient. So we've talked about service coordination, making sure our services, say, in that laboratory installation are good to go. And same for, say, the cloud installation for the control plane. Now, how do we go about the deployment for our healthcare use case, given we're going to be deploying to a lab, and then wherever else we want the control plane? How do we go about the deployment given two systems with two operating systems? Well, we're still in the develop and code phase of our software development lifecycle, so let's take a peek. So we did have a few considerations going into the deployment thought process. We had additional hardware. I think I had 4 computers during this project, and one of which was a Windows machine, because we needed to simulate what that lab was running. We also wanted a unified deployment process, and then we also wanted to minimize requirements for software dependencies, right? Minimize the effort for our deployment process. That brings us to the first tool that we worked with for our data plane deployment, which is this Go MSI package. Again, it's that initial tool we chose. The features include generating an MSI package for Go projects. Who knows what Go MSI stands for? Or sorry, MSI, it's an acronym. Anyone? Yes, everyone knows, Microsoft Software Installer. Yeah, well, not everyone knows that. I learned that working with this. And so basically, it is a package that enables you to take your Go services and make it easy to deploy it onto a Windows machine. With a really nice little UI, you can click through and say install, upgrade, really nice little UI. And it also came with a CLI for the Go MSI package. And our team, I wouldn't say we were Windows Go experts. So this was a nice CLI tool where we could do things like check our environment configs and so forth. So that was a nicety. And there were 3 steps here for the Go MSI package. First of which was creating a wix.json. This is simply a configuration file to describe packaging rules for that resulting MSI file. We then generated GUIDs, or globally unique identifiers, for our different services for the Windows machine. And then from there, we would use that Go MSI CLI to generate our MSI package. So a few steps, and that's where we started to learn some of the overhead with this package. Who knows what Wix stands for? It sounds like Dylan knows. But Wix is basically a tool set that lets developers create installers for the Windows installer engine. And it also had additional installation requirements. So we had to add this to the path, right? Install it, add it to the path for our data plane. But it had 2 other tools that needed to be installed as well. Can y'all guess what they're called? Candle and Light. I don't know why, but Candle is a Wix tool to pre-process and compile Wix source files into object files. And Light links and binds one or more of those Wix object files and creates a Windows installer database. So it's kind of just a bit of mental overhead with respect to this package. And we also in the future wanted to support Windows 11 as well in the laboratory environment, but I could not get it to work. And we also had additional requirements to be installed due to the Go MSI package, so it was just kind of a lot of overhead on the team. So we wanted to think, is there a simpler approach to take? Y'all think we found one? Yeah, we did. So we added one more step, but I think it simplified things on our team. For the data plane deployment steps, what we did is we ended up building our executables, copying them over to a zip folder on a USB drive, copied that folder from the USB onto the data plane, and then we would use PowerShell to start our services using .bat files. And so .bat files are just basically a script file where it will store commands to be ran in serial order. So simpler and easier on us as a team. From there, the control plane had also 4 steps, where we would build our executables, generate our Docker artifacts, because we actually had Docker here, grab that IP, and then we would use our make commands to start our services using that IP. So you can see it's kind of a more unified approach, simpler on our team, and included learnings along the way. Sometimes change is good, y'all. We started with the Go MSI package, and then we wanted to switch to a different approach using .bat files. This made sense for our team and our customers, those bench scientists, right? We didn't want a complicated deployment process. We wanted it to be as simple and harmonious as possible. So the switch was good for everyone. Also for our deployment, we had some automation difficulties. So we did have some tool churn. When we were going about our CI/CD pipeline, we initially, in our org, used Jenkins. And then we had to duplicate the work because we talked about open sourcing this project and had to set up GitHub Actions runners. So duplicate work there. And then we also had a learning curve with respect to Windows GitHub Action runners since our data plane had Windows. And this also meant increasing our test time, right? Which is the perfect segue into the next step of the software development lifecycle, which is testing our healthcare use case with 2 systems and a lot of microservices, right? So we're at the test phase of the SDLC, which included a few components. Many of these I definitely went much more in depth on last year for an integration testing presentation. So this year I kept it a bit higher level because I'm covering a lot of ground. The first part was the integration tests, so setting up your test dependencies. And for that we use test containers Go. The second part is actually doing your test cases, the assertions. And for that we used HTTP expect. And lastly, our stakeholders wanted some sort of a test artifact, which we used the Go test report tool for. And to touch on each of those tools, the test containers for Go package is really awesome because it's a part of a much larger test containers community for spinning up your test environment and services, right? So it's got a few different features such as garbage collection and a really nice way for you to test what you're actually deploying. And it did the trick for us. So what that looked like from a coding perspective, we used their Docker Compose module just because we were using Docker Compose for our solution. And so you can see there, step 1, I've defined, hey, here are my Docker Compose files. Step 2, we added a wrapper to start our services. So this called the underlying test containers Go code to set up everything, apply weighting, apply other configuration that we wanted. Then step 3, we would actually execute our test cases. And step 4, clean up. That's probably good. Next, once you set up your test services and you're ready to actually run those test cases, you can use HTTP expect for your test assertions. And that's what we did. It is a concise, declarative, and easy to use HTTP and REST API testing package. It supports things like chainable builders and assertions on HTTP responses and payloads. So what this looks like, at a quick glance, this is a simple test case. The first line within the function sets up an HTTP client to make requests to our pipeline simulator. We then run a GET request to our job endpoint with a specified max retry and retry policy, right? It's that chainable builder there. Then we make a set of expectations on our response to include a status OK, which makes sense, and then asserting on the empty JSON array, since at this time we had no jobs. And from there, we added a bunch of other tests for our solution, and then we got to a point where we needed to prove to stakeholders, hey, it works as expected. And that's where we talked and worked with the Go test report tool. So this parses your Go test output into a single self-contained HTML file, and that's what we used to give us that project requirement. And what that looked like from a code perspective, we added this into our make file. And you can see there, we have the native Go test framework. We are specifying the JSON flag. And then we pipe that to the Go test report tool to give us the HTML report for our stakeholders. Many learnings, as always. And I want to ask y'all, how many of you have dealt with idempotency issues or non-deterministic results? Okay, everyone's hand should be raised, honestly. Yeah, it's a booger. So for us, we were passing files around, checking statuses, and so forth. And so when it came to our testing setup, we dealt with a lot of idempotency issues, unfortunately. Say between the transfer of a file from, say, the laboratory environment to the control plane, Maybe for my machine, it took 3 seconds, and the test worked fine, but my partner in crime, Neetu, for her machine, it didn't work, and so she had to bump up the sleep to like 5 seconds. So we just kind of all battled with this as a team, trying to find a happy path here to get more consistent test passing results. And it got me thinking, what are things that are actually within our control? Because I think we see this time and time again, and it doesn't matter the use case or the project. It's just there are some things that are within our control and some things that aren't. So what is within our control to alleviate some of these idempotency issues? Well, there's a few. One of the first things that, honestly, I try just to see if things will pass is adding explicit waits with a time.sleep. I think that's a really simple, easy win if it will get the job done. There's also things like retry mechanisms or isolating different components to see if that will help. So there's a few things that are actually within our control that we can do or check to improve idempotency issues. And there are also things outside of our control, unfortunately, such as network and connectivity issues. So mapping back to that healthcare use case, we had 2 systems and a lot of microservices in both. So we did have firewall rule restrictions, but maybe in our testing environment, there were just some network and communication issues that we couldn't necessarily replicate locally. Those are hard, really hard to fix and replicate across team members and so forth. And there are also just external dependencies that you might have or shared environments. So it's just kind of hard sometimes when it comes to these idempotency issues, and you just got to look at what you can fix and try that. So that's my big learning for this section. I saw nodding heads, so I think y'all agree. Idempotency issues are normal, sometimes. And you should always just focus on what you can control to make incremental improvements. And also knowing your toolbox. So this section made me realize that there are just some Go packages that I have in my back pocket, and I'm like, this will get the job done and do it good. And lastly, as a team, we had a lot of learnings when it came to Go in a Windows environment from a tooling perspective, deployment perspective, just kind of overall a lot of learnings. And my last part before I get to the conclusion is really fun. It is internationalization, or the supporting of multiple languages. How many of you know how many letters are in the word internationalization? Nice. Okay, some people just know. Other people are counting. It's 18. So internationalization is abbreviated with I-18N. That is my fun fact of the day for y'all. And this brings us to that maintenance phase of the software development lifecycle, where our product team got some additional requirements where they were like, hey, we need to support Chinese for the web UI. And so we had to look into how the heck do we bring this into our healthcare solution and all of our microservices. And that actually brings up a kind of different word here under the same space, which is localization. So internationalization is a bit broader with respect to bringing in the flexibility in your software to support many languages. Localization is much more specific, supporting specific localities. So we had a need for localization to Chinese for bench scientists who spoke Chinese. So you can see here, we have scientists. They have their cellular images. We are doing some processing and enabling this whole pipeline for them, generating those outputs. Like y'all have seen this. But now it needs to be translated. And so we had to look, what do we need to translate? And so we looked at what are the pieces of our user interface. Well, that breaks down to task creation, which are where those bench scientists will say, hey, I have input images, here's my cellular data, please add these pipelines to execute. We also had job monitoring, which is where you can see the status information, get information on your input images or your output images, and maybe error details if there's a transient issue or something. And then we had observability. So let's hone in on that job monitoring. Here is where I'm displaying some job-related information. So hopefully it's not too blurry. But basically there's a few jobs, there's status information, there's ownership information of where things are at in our system. and there's input and output file information for you. And it is all of this dynamic backend data that we needed to localize to Chinese. So really fun problem. And that brought us to this Go package called Go I18N. This is the package that we use for our dynamic data to be translated to Chinese. So it's really awesome because it supports pluralized strings for over 200 languages. In the Unicode Common Local Data Repository, which is a comprehensive and widely used repository for locale and language information, maintained by the Unicode Consortium. So that was a mouthful, but reading that helped me see that this is really good. Like, it's backed by some really good stuff, and it seems like a good package based on some of the GitHub badging you see there. So the thing that we had to change was adding a header, and then it would work. Well, with some backend changes, right? But we would add this accept language header, and then we would specify NZH for in Chinese. And so the main steps here included defining a language bundle, loading our translations, creating a localizer, and then seeing those translations. So what that looks from a coding perspective, we had a translation package, and we would define a new bundler for our controller to translate the job-related information. We would load in those translations pointing to our dictionaries. So you can see that with the load message file function. We created our localizer. So you can see here we have a translate function for our jobs. And we are calling a translate field function that we have defined. And then from there, we actually translate the fields using that Go I18N package. And you can actually see here there is a message ID. So what this does is it kind of maps the keys across your different dictionaries, and then based on the header that you have chosen, it will translate based on your dictionaries, right? So it's all of these different steps is how you go about this implementation. And lastly, there were some learnings on this as well. You can see here part of our dictionary. So this is what it looked like in English. So in green, we have keys or message IDs. And then in blue are the translations. So here's it in English. You can see status information, file status information, pipeline status information. So we had a lot of statuses. And then we had owners, and then we actually added an abstraction layer here where we were only bubbling up some errors because our bench scientists did not need to know everything, right? And from there, we would add dictionaries for each language we wanted to support. For us, we needed to localize to Chinese. So you see the green is the same in terms of those keys, and then you have the blue, which is the translation. And you can see how this can kind of scale to become a lot of maintenance on the team. The dictionary can grow in length based on the keys and the message IDs you want to translate. And it can also scale out depending on how many languages you need to support. So there were also a lot of learnings on this one. There are very few package options, I would say, on a Go perspective if you need to internationalize things. But thankfully for everyone here, the Go I18N package is pretty great, and also looking for maintainers if y'all are interested. This also included code bloat and maintenance for us, because y'all saw the dictionaries can get big, and it can kind of get messy. And so it also brought into play, how do we go about branching? Do we want all of this going into main? Do we want different release branches? Do we want to separate these out based on languages? So there were a lot of considerations we went into open-minded as a team and with our eyes wide open, right? Third, there were team collaborations because, I don't know Chinese, and so I need to rely on someone who does for this so that our bench scientists know what they're actually getting for their cellular input and outputs. And so, because of having to work with external teams, this can include additional costs on project, which sometimes can be a showstopper. And then lastly, knowing where to draw the line when it comes to what to internationalize is sometimes really hard. So for us, it doesn't make sense to translate logs. Like, debug logs, that would not make sense. But, there were things that did make sense. So that depends on your use case. And for ours, I kind of showed y'all some of what we translated. Whew, we've covered a lot. Now we'll go ahead and wrap things up. We have covered the full software development lifecycle for this healthcare use case, which was really fun. And we went from an introduction covering some of that planning and some of the scope around this down to the maintenance, where we had some additional requirements for internationalization. We covered this healthcare use case for Go in the machine learning space, where we had these microscopes, these bench scientists generating cellular input images, passing it off to our control plane for processing, generating outputs. This was most of our solution, right? Simplified. And a cool project means cool packages. So we saw for service coordination that wait for it Go package. For deployment, we saw the Go MSI package that we then switched away from to a more PowerShell and .bat file approach for the data plane, and the control plane included Docker and make commands. For testing, we saw 3 packages: the test containers for Go package, HTTP expect, and the Go test report package. And then for internationalization, we saw that Go I18N package. My takeaways for y'all. Hopefully y'all see also that data processing is really good for Go. It's really easy with Go, right? And you can also create really meaningful projects that are enabled by Go. This had some very real human impact, working with cellular images, breaking down the time and making it to where you could reuse by virtually staining instead of physically staining the specimen. And hopefully y'all are also seeing some really awesome package insights in case you ever have to internationalize your project or work more on the Windows side. And hopefully you've learned from some of our successes as a team, as well as some of our mistakes, because that is absolutely the point of conferences and these talks and networking. And then be fearless with your Go use cases always, because we do not have to fit into a box. I'm proposing that Go is great for data processing, and hope all of y'all agree. So if you want to know more, here is a page for more context. There's also the open source repository available at that link for number 2. Number 3 is an open source summit presentation on the open source components, shedding a bit more light on that black box of the machine learning processing. Step 4, 4 are the slides I will upload shortly. And then if you want to read blogs, if you like blogs, there's more information on service coordination at my website. So thank you all so much. My name is Samantha Coyle. I'm a software engineer at Digrid, and I really enjoyed y'all's engagement in coming to my session for Go Microservices for Machine Learning at the Edge. Enjoy the rest of GopherCon. Thanks.